Recently, the idea that our universe and we both live inside a black hole has been gaining popularity. These mysterious monsters distort space and time to such an extent that they change their places, and what is most amazing is that this idea is not as crazy as it seems. Let's try to figure it out and try to understand it. But first, I advise you to set up your brain for thinking purity. The defining feature of a black hole is the presence of an event horizon, a boundary that tells a completely different story for an object beyond it than for an object inside beyond the horizon. Any object will experience its gravitational effects. Since space will be curved by the presence of a black hole, it would seem unrealistic to escape from such tenacious clutches. However, under certain circumstances, it is still possible if the object moves fast enough or accelerates fast enough in the right direction. It will not necessarily fall into the black hole and can escape from its gravitational influence. However, if such an object is unlucky and it still crosses the event horizon, then almost instantly it is doomed to be included in the central singularity of a black hole. Because how strongly the fabric of space-time is bent inside it, the falling object will reach a singularity within a few seconds after crossing the event horizon, while increasing the mass of the black hole for someone who is outside the event horizon, and the black hole will seem to be forming, gaining mass and increasing over time. But what does our universe have to do with it if we take all known measurable forms of matter and radiation in the observable universe? It turns out something like this. There is ordinary baryonic matter consisting of protons, neutrons, and electrons. There are ghostly neutrinos, fundamental particles that rarely interact with ordinary matter. Dark matter is the dominant mass force in the universe, but has so far eluded direct detection. There are also photons or particles of light that carry energy from every electromagnetic event throughout cosmic history, and finally gravitational waves that are created every time mass moves and accelerates through the curved fabric of space-time. The farthest limit of what our instruments can detect today ends at a distance of about 46 billion light-years in all directions. If you add up all the energy across the entire observable universe using probably the most famous equation here, you get the equivalent mass of the universe now we need. To ask a pretty deep question, if the entire universe were compressed into one point, so that the answer would be the same as if you compressed any sufficiently large set of mass or energy into one point if a black hole in the theory of gravity is interesting, here's what kind of thing if it is a collection of mass and or energy that is not electrically charged and does not rotate without angular momentum, then the total amount of mass is the only one. The factor that determines the size of a black hole is what we today call the Schwarzschild radius. It is noteworthy that this radius of a black hole, with the mass of all matter in the observable universe, is almost exactly equal to its observable size. This realization in itself seems to be a remarkable coincidence that raises the question of whether our universe can really be the inner space of a black hole. But this is only the beginning of the story. The deeper we dive, the more interesting it becomes. In the middle of the 1960s, a discovery was made that revolutionized our ideas about the universe is homogeneous. A directional bath of low-energy radiation has been detected at all points in the sky. This radiation has the same temperature in all directions. 2 whole 725 thousandths. Kelvin, just a few degrees above absolute zero radiation, has an almost perfect spectrum of a black body, as if it had a hot thermal origin, and looks identical to an accuracy of 1 part on 30,000. No matter what part of the sky you are looking at, this radiation, now known as the cosmic microwave background, represents decisive evidence that our universe is expanding and cooling, because in the past it was hotter and denser the further back we extrapolate, the smaller, more homogeneous and compact the objects were. Going back to the past, this picture of a hot Big Bang seems to be approaching a singularity to the same state as in the central bowels of black holes, a place where the densities of temperature and energy are so it is extreme that the laws of physics are violated. Let's say we are just beyond the event horizon and go an infinite distance from the black hole. which turns out we will find that the distance goes from the Schwarzschild radius to infinity. On the other hand, if we are right inside the event horizon and start tracking the distance from the black hole to the central singularity, we will find that the same distance instead goes from the Schwarzschild radius to 0. This actually makes a lot of difference if we study all the properties of space outside the event horizon of a black hole from radius to infinity, and compare them with all the properties of the space inside the event horizon from radius to 0. Then they must be identical at each point, that is, the interior of the black. The hole is mathematically identical to its appearance. Our understanding of the universe was greatly facilitated by two discoveries. The first is this cosmic inflation instead of arising from a singularity. Now it seems that the universe was created in a rapid, steady state of constant exponential expansion that preceded the hot Big Bang, as if there is some kind of field that provides energy inherent in the cosmos itself, causing the universe to inflate, and only when inflation. The hot Big Bang has ended, and the second discovery is this dark energy as the universe expands and becomes less dense. Distant galaxies begin to move away from us with acceleration. The universe behaves as if there is some kind of energy inherent in space itself. That is, it may be that dark energy is the result of a spatial topology inherited from a black hole. There is also an assumption that there is a connection between inflation and dark energy, but what is this connection? And again, black holes may be the answer. They gain mass as matter enters them and disintegrate, losing mass under the influence of Hawking radiation as the size of the event horizon changes. Can the energy inherent in the fabric of space change for an observer inside the event horizon and what we call cosmic inflation? Does this mark the creation of our universe? And supermassive black holes, is it possible that dark energy is also somehow related to black holes? And does this mean that as astrophysical black holes formed in our universe, each of them generates its own small universe somewhere inside it? These assumptions have been around for many decades, but without a definitive or provable conclusion nevertheless. There are many models, and this line of thought continues to attract many who explore black holes, thermodynamics and entropy, general relativity, and the beginning and end of the universe. Unfortunately, no advanced physical model, at least so far, has been able to provide accurate answers. Perhaps the most famous attempt is Roger Penrose's cyclic cosmology, which really gives a unique assumption other than the standard cosmological model of the existence of Hawking points. With an unusually low temperature dispersion on a cosmic microwave background, undoubtedly there is something in this idea between a black hole and the birth of the universe too, that there is some kind of connection. It is likely that there are connections between the birth of our universe and the formation of an extremely massive black hole from the universe that existed before ours. It is possible that every black hole formed in our universe gives rise to a new one. We do not know if the universe is from a black hole, but at the moment there is such a tempting possibility that it would be foolish to deny, regardless of whether this provocative theory is true. But black holes are the key to understanding many mysteries of the universe, including the Big Bang inflation and dark energy, the highest temperature of the Earth's surface for many years of observation, and fixed at almost 71 degrees Celsius. It's too hot to even pronounce, not to feel it. Meanwhile, the record of the Earth, but not the planets of the solar system, is the same Venus. Despite the fact that it is the second hottest planet of our system from the Sun, the temperature here reaches some insane figures of 460 degrees Celsius, but this indicator is a trifle against the background of the temperature of our star, which reaches 5,500 degrees. However, you can go even further and compare this temperature with the temperature of other stars, which have this indicator hundreds or even thousands of times higher. But even there, it is not so hot because there are quasars whose centers emit more energy than the entire Milky Way taken together. The temperature of gases in the Russian Federation to quasars can reach 80 million degrees, so you can compare it for a very long time to constantly find examples where it will be hotter and hotter. But we thought about this. And if at all the limit of high temperature, see the limit of low temperature is minus 273 whole and 1500 degrees Celsius or 0 Kelvin. So it would be more correct. It is also called absolute zero. As you may know, movement causes friction that causes heat. So absolute zero is essentially the moment when all movement stops. And if such a zero exists, then if the opposite is the so-called absolute heat. Stop any movement is one thing. But how to measure maximum movement? How do we bring energy to infinity? Let's try this. It will not be easy to find out. Though, and I will say right away that we will mention the Big Bang next, so I suggest that the opponent of this theory close this terrible video so as not to injure your fragile psyche. But for everyone else, welcome. This will be a very hot issue. Get ready for mind-blowing numbers. It will be interesting, so put your finger up under this video right now and go towards we should start with high temperatures from the end of the 19th century. It was during this period that German physicists, concurrently the founder of quantum theory, Max Planck, proposed a special measure of measurement is the Planck units, a unit designed to simplify certain algebraic expressions present in theoretical physics, and in particular in quantum mechanics. They include such fundamental units as mass, temperature, length, and time. And later, they were all combined into one Planck epoch according to the standard cosmological model. The universe was born as a result of the Big Bang, which began in an infinitely dense. At the point, it was the earliest stage of the formation of the universe that can be theoretically justified and described. This is Planck's epoch. To understand what quantities we are talking about, you can look into the animation scale of the universe at the link in the description under this video. So according to the Big Bang theory, the universe had a Planck temperature at the end of this epoch during the first 10⁻43rd degree seconds of the universe's existence during this period, literally in the blink of an eye. Planck time is natural and spatial. The time continuum reaches a state known as absolute heat. The temperature at that moment was 141 in 1,679 actor Leon Kelvin, or approximately 250,000 billion degrees Celsius. This indicator is the upper limit of the possible temperature at which quantum theory works. Nothing can be hotter due to a significant increase in particle energy. With an increase in temperature above this limit, gravitational forces will become on a par with other types of interaction, that is, gravity and three other fundamental forces of the universe. Electromagnetism is strong, and the weak nuclear interactions become a single unified force to describe a substance in a hotter state. The quantum theory of gravity, which is still being worked on, but nevertheless the best models of the origin of the universe based on the Big Bang theory, suggest, as we have already found out, that the universe passed through the Planck temperature during Planck time, literally a minimum fraction of a second as a result of the huge expansion of entropy. From this moment, our universe grows and cools, but it was only one version. And what does the other string theory tell us, according to which our universe basically consists not of particles, but of tiny vibrating strings, has own opinion about the maximum temperature in the model of this theory? The early universe is very different from traditional models and the Big Bang. Cosmologists call it the string gas model. It sets the maximum temperature called the Hagedorn temperature in honor of the German physicist. And although string theorists do not give a specific number for this temperature, which may be correct, there is reason to believe that this is about 1% of his theoretical brother Planck, that is, about 10 to the 30th degree Kelvin, which is 2 orders of magnitude lower than the Planck temperature. Here the maximum temperature predicted by string theory will be expressed. Come on, these are all theories, and calculations will still be recalculated 100 and 500 times and will change. There is some real figure of high temperatures, and we will answer you, yes, it is certainly far from the Planck temperature, and even from the temperature of string theorists, but still, it shocks not so long ago in the 2010 year. Scientists created the highest temperature in the CERN laboratory, known by the European Organization for Nuclear Research. For this, they collided gold particles with each other for a fraction of a second, and as a result, the temperature it has reached almost 6 trillion kelvins, which is absolutely amazing and unique, because this indicator is hotter than the temperature during a supernova explosion. Of course, it is incredibly hot, but is this indicator a limit created artificially? In other words, can we at least reach the temperature of the bar is not to exceed it. But the problem here is that the final goal is so high that no foreseeable experiment will ever be able to reach the final temperature of the bar, not to exceed it. And this temperature is so huge that there is not a single known natural phenomenon that even approaches it. Eventually it can happen, but only when the particles will reach the so-called thermal equilibrium that the entire universe and all its objects should achieve. But is it possible in reality? I think the answer is obvious. I hope you liked this issue. If so, put your finger up under this video, subscribe to our channel, who is not with us yet, and see you again. One of the most frequently asked questions in the comments on our channel sounds something like how a Big Bang could form out of nothing. In other words, how the whole universe that we observe today could appear out of nothing. Of course, this question has the right to... Its existence is quite logical because firstly, we quite often rely on the Big Bang theory in our videos, and secondly, no matter how contradictory the theory itself is imperfect. Therefore, similar questions arise for those who are not familiar with it, who have not tried to figure it out and understand it. But when questions remain unanswered for a long time, they begin to grow with all sorts of conspiracy theories, sometimes even absurd. What can you do? This is how a person works if he does not fully understand something. Then he looks for a conspiracy in this, because it is easier to believe in this than in a complex one. The scientific processes that seem incomprehensible, we will try to answer this question, but with reservations. Firstly, all that you will hear is purely the opinion of our channel. If you do not agree with this opinion, this is your right, and secondly, often those who write how a big one could happen, and then they write something like nothing is incomprehensibly difficult. And so on. Guys, yes, this is not an easy topic. This is not popcorn content for you. Of course, we will try to explain it as simply as possible, but if you do not understand something, review the video. Look for the answer in Google to the question that we could not understand. It is normal when we do not understand something, but we are trying to figure it out. It's called self-development. Just imagine, people have been puzzling over the mystery of why the universe exists for thousands of years. Almost every ancient culture considered it an immediate duty to come up with its own story of the creation of the world, and most of them came to the conclusion that the gods had a hand in the creation of the universe from a scientific point of view. So far, everything is not so clear. Science has generally said little else about it, but in recent years, things have moved forward. Some physicists and cosmologists believe that we have an understanding of the history of the universe and the physical laws that describe how it works. The key to understanding how and why space exists the entire universe, from the Big Bang to the star-studded cosmos in which we now live, arose from nothing. There is an opinion that this should have happened because nothing this idea is inherently unstable. It may seem strange, it's just like another story. Only there, the gods created, and then this and that appeared out of nothing, you know. But the fact that the Big Bang occurred naturally follows from two of the most powerful of the most successful theories of science: quantum mechanics and general relativity. And let's see, first, quantum mechanics is a branch of physics that deals with very small things, atoms and even smaller particles. It is an extremely successful theory that underlies most modern electronic devices. Quantum mechanics tells us that empty space does not exist. Even a perfect vacuum is actually filled with a swirling cloud of particles and antiparticles that flare up and almost instantly disappear into nothing. These particles do not exist long enough to be observed directly, but we know that they exist by the effect they create from tiny things, such as atoms, to really large, huge ones, such as our galaxy cluster in the context of the Earth, and not a single country. The best theory for describing such large-scale structures is the general theory of relativity, Einstein's theory of relativity, which establishes how space-time and gravity work in space, is very different from quantum mechanics. So far, no one has been able to fully combine both theories, but it has already been possible to apply both theories to solving specific problems. For example, Stephen Hawking used them to describe black holes, and one interesting detail turned out when quantum theory is applied to space in the minimum possible. At scale, space itself becomes unstable instead of remaining perfectly smooth and continuous. Space and time become destabilized by churning into foam from the bubbles of space. Time, in other words, these small bubbles can form spontaneously, so you can create a virtual space-time in quantum physics. If something is not forbidden, it necessarily happens nevertheless. It looks like some kind of huge leap from an infinitesimal point in space-time to a massive universe containing trillions of galaxies. If a bubble formed, it would be doomed to disappear again. In fact, no, this bubble can survive, but for this, it will need cosmic inflation. Many of our viewers think that the universe began directly with the Big Bang. At first, all the matter and energy in the universe were compressed into one unimaginably small point. It crashed, and then everything started mixing up. People, horses, stars, clusters, and so on. And this all follows from the discovery at the beginning of the 20th century that the universe is expanding if all galaxies fly apart. Then the theory of inflation suggests that immediately after the Big Bang, the universe expanded much faster than it is. Now the idea is that a fraction of a second after the Big Bang, the cosmic bubble of quantum dimensions expanded enormously quickly in an incredibly short moment. It turned from smaller than the nucleus of an atom to the size of a grain of sand when the expansion finally slowed down the force field that powered it, turned into matter and energy that today fill the universe strangely enough. But inflation corresponds quite well to reality in particular. This clearly explains the cosmic microwave background weak. The radiation residue left over from the Big Bang inflation has also given cosmologists the measurement tool they need to determine the geometry of the universe turns out to be also important for understanding how the universe arose from nothing. General relativity tells us that the space-time in which we live can take three different forms. It can be as flat as jokes about a black hole in a former one. It can also bend back like the surface of a sphere. And in this case, if you go far enough in the same direction, you will return to where you started from. Now you understand why those who we send away for some reason do not go anywhere. They will just come back physics, and also space-time could bend like a saddle. Perhaps you remember from the math lesson that the angles of a triangle add up to exactly 180 degrees. In fact, there is one important point. All this is true, but only for a flat surface. If you draw a triangle on the surface of the balloon, its three angles will total more than 180 degrees. And if you draw a triangle on a surface that bends outward like a saddle, its angles will total less than 180 degrees. And so to find out if the universe is flat or not, we need to do what we need to measure the angles of a really huge triangle. Here, we need cosmic inflation. It determines the average size of warmer and colder spots on the cosmic microwave background. These spots were measured in 2003, and this gave astronomers the opportunity to choose the angles of the triangle. As a result, we know that at the largest observable scale, our universe is flat. It turns out that a flat universe is crucial, This is because only a flat universe could probably have arisen from nothing. Everything that exists, from stars and galaxies to the light they emit, must appear from somewhere. We already know that particles arise at the quantum level, but to create all these stars and planets requires a huge, colossal amount of energy from where the universe took it. Every object in the universe creates gravity by attracting other objects to itself. This balances the energy needed in the first place. To create matter, physicists calculated that in a flat universe, the energy of matter is exactly balanced by energy by gravity. Again, this is all true, but only for a flat universe. Quantum mechanics, it tells us that nothing is stable by nature, so the initial leap from nothing to something could be inevitable. Then, the resulting tiny bubble of space-time could result in a massive loaded universe due to cosmic inflation. The laws of physics as we understand them make it highly plausible that our universe originated from nothing nor space. There was no time or particles, nothing that we now know about. Then why did it happen only once if a bubble of space-time arose and swelled to form our universe? What was in the way other bubbles do the same when the new universe stops inflating? It is still surrounded by space that continues to expand. This expanding space can give rise to more universes, and there will be even more inflating space around them. And since inflation is just beginning, it should form an endless cascade of universes that physicists call eternal inflation. Our universe may just be a grain of sand on an endless beach. Such universes can be very different from ours. Some may have 5 spatial dimensions rather than 3, as we may have gravity 10 times stronger or 1,000 times weaker or not at all. Matter can consist of completely different particles until we have convincing evidence of the existence of a multiverse. But I hope now the answer to the very question has become at least a little clearer: how the whole universe could have appeared out of nothing at the beginning of the last decade. A very important event occurred. The European Centre for Nuclear Research, or abbreviated CERN, announced the existence of the long-awaited Higgs boson in the scientific world. It caused a real furor. A new chapter in physics was opened at the same time. Some answers were given important questions related to the existence of the universe. What is so important here, and why the Higgs boson is often called the God particle? We will try to tell you about it in simple language. But if you think that you can make it easier and better, write your versions in the comments, because we believe that it is very simple to do this. It is not at all easy to start first from the two concepts of particle and force. It is on these two foundations that the whole world stands, on these two pillars. The entire universe, everything from small objects to large galaxies, is the sum of particles and the functional forces between them. The whole world has been stabilized. The universe is driven by the interaction of particles and forces. What is a particle in front of you? An electron. It is considered one of the elementary particles. These are those that can no longer be broken into small parts, and these are proton and neutron. We can no longer classify them as elementary because they can still be divided into several quarks according to the information known so far. A quark, this is a fundamental particle. Physicists created a special theory to better understand this incredible world of particles and called it simply the Standard Model. It describes the electromagnetic interaction of all elementary particles, weak and strong, but it does not describe some aspects of physics. For example, dark matter, which is why it cannot be called a theory of everything. The picture of the Standard Model fully developed only when the Higgs boson was discovered. We can divide the Standard Model into two main parts: fermions and bosons. Fermions are the building blocks of our universe. They meet with each other to form all objects. Matter, but bosons are the main force particles. They control how and where the forces of the universe work. Fermions are divided into two categories: quarks and leptons, each of which in turn is divided into 6 types. The main difference between them is that quarks feel force and leptons do not, but the boson is a particle of force. This includes the graviton, photon, gluon, and boson. There are 4 fundamental forces of nature. This electromagnetic force is strong, nuclear force, weak nuclear force, and gravitational force. Graviton is considered a carrier of the latter named forces, although there is no confirmed evidence of the existence of this particle, yet it was found. But scientists believe that it must exist. Then, it carries the magnetic energy of fire. It carries strong nuclear forces holding together neutrons and a proton nucleus, but boson's responsible for the weak nuclear forces, and here another type of these particles comes into play, the Higgs boson. The first thing that follows the concept of force and particles is this mass, which is the main reason for the existence of the universe. If there were no mass in the universe, no small objects could be formed. But where does the mass in these main parts come from? The formation of an object, there is a small correction here. Not every particle has a mass. It is the Higgs boson that could help explain how these particles get their mass in the 1960s. Peter Higgs is the same physicist after whom the elusive particle was named. He developed a theory explaining how particles carrying electromagnetic or weak interaction could get different masses during the gradual cooling of the universe. His assumption was that particles like protons, neutrons, and quarks get mass through interacting with an invisible electromagnetic field known as the Higgs field. Some particles are able to pass through this field without getting mass in, while others get stuck in it, and accumulate its mass depends on how much the object interacts with this field. For example, particles, photons, do not interact with the field when crossing it. This causes the photon not to gain mass. Quarks, on the other hand, crossing the fields, enter into direct interaction with it, which leads to the formation of mass. But how is the Higgs boson related to the Higgs field in quantum physics? All basic particles have different fields, and our entire universe is covered with them. Moreover, they all interact if these fields are stirred up. The particles or waves associated with this field will come out and manifest themselves, which means they can be observed. For example, photons manifest themselves in the same way during magnetic field disturbances. The Higgs boson is a particle associated with the field of the same name, and this is its smallest part. When a scientist expressed the idea of the Higgs field, the scientific world did not recognize it. Not because there were mistakes, but because no one could digest that information. The fact that an invisible field gives strength to particles. Later, many studies were conducted based on the mathematical equation of the scientist, but no one has discovered anything. The fact is that the Higgs boson quickly decays into more stable particles. It is more difficult to observe than others produced during the collision process, and in accelerators, it is believed that up to it exists for only 1/100th of a second, which seriously complicates the work of detecting it among those trillions of collisions. Subatomic particles are generally extremely difficult to observe because of their size. They are smaller than an atom and the wavelength of visible light. The only way available to us to register and observe their behavior is to collide atomic nuclei consisting of particles with each other at incredible speeds close to the speed of light. This produces a large number of exotic particles that are created only at high energies. Physicists believe that these collisions remind us of the conditions under which the universe developed immediately after the Big Bang. That's what the largest particle accelerator, the Large Hadron Collider, was needed for. Built in the year 2008, the work was not easy, but finally in the year 2012, it was discovered that a new particle, almost equivalent to the conceptual Higgs mass as a result, ensured the existence of the desired particle. And when scientists from CERN announced the discovery of the Higgs boson, they actually proved that there is also a field of the same name to obtain evidence of the existence of the boson and the Higgs field, an important discovery for all physics. The universe would not exist without them, and therefore we would not exist. But what does it give us now? No, the Higgs boson will not allow us to travel in time. It will contribute to the creation of a perpetual motion machine and will not become the basis for a cure for all diseases. In fact, its discovery simply confirmed the supposed principles of particle interaction and brought together all the statements of the Standard Model. It is likely that due to its appearance of questions in other areas of physics. On the contrary, it will only become more of course. It does not give us ordinary people anything, but it is important for fundamental physics for science, which means that humanity is still moving forward in its development, which is already good. We have already realized that the Higgs bosons confirm an important reason for the existence of this. However, this has nothing to do with God, in fact. Such a name is generally an accident. Scientists realize that the Higgs field must exist because otherwise the Standard Model of physics will not be complete, and the reasons for the increase in the mass of the main cells cannot be explained. And since Peter Higgs gave the world this idea, scientists have been trying to find the elusive particle. But all unsuccessfully. At the beginning of the 1990s, another physicist, Nobel Prize winner Leo Laserman, wrote a whole book about it, and either out of desperation or in his hearts, generally freaked out and called it the cursed particle to the publisher. He didn't like the name of the book. He thought it was commercially unattractive and decided to rename the book. Apparently he was right because the new name stuck, and since then the Higgs boson has been known to most people as a particle of God. By the way, it is worth noting that there is even a whole boson star, hypothetical like quark stars. However, this is a completely different topic for a separate video. If you're interested, let's like this video and write about it in the comments, and then these stars will stop being hypothetical and become real. But on our channel, of course, we will not be able to light them in the universe in any way. The choice is up to you. Until new interesting meetings, black holes are in many ways the most extreme objects in the universe. They literally pack a huge mass into a smaller volume of space and bending the fabric of space so much that as soon as something enters a certain area, it can never escape, even if it moves from the ultimate cosmic speed is the speed of light. Apparently, trillions of black holes are distributed in every galaxy of the universe, like the Milky Way, and the largest of them reach billions. And yet, if we think about how all these black holes were formed, then we can say quite confidently that each of them was originally made of ordinary matter. None of them formed from dark matter, even though dark matter exceeds the usual 5-to-1 ratio in the universe. But if black holes are the result gravitational force, if dark matter reacts to it, then what prevents the formation of a black hole from dark matter today? We have a cosmic story about whether black holes can consist of dark matter, and if not, why the modern universe knows only a few ways to form black holes. Perhaps the most common method is the collapse of the core of an extremely massive star. The only thing that keeps stars from gravitational collapse is the energy produced by nuclear fusion in their cores, where the external radiation pressure balances the internal gravitational force. When the core of a star runs out of fuel that it burns, the radiation pressure begins to fall, and the core of the star begins to contract under the influence of its own gravity. When compressed, the core of the star heats up to temperatures that a simple viewer It is even difficult to imagine. The higher the temperature becomes, the more likely it is that the core can start burning even heavier elements using them as fuel. And after these elements are exhausted, the core will collapse as a result of a supernova of the second type. While if it is massive enough, a black hole will form due to the accumulation of huge mass in such a tiny volume of space. But if the core is not massive enough, a neutron star will be born. In addition, a black hole may still form as a result of the collision of two neutron stars, provided that the total mass after the merger exceeds a certain threshold. And finally, a black hole can form as a result of direct collapse when, for example, a single massive star simply becomes too dense for light to escape from a certain volume of space. As soon as this condition is met, an event horizon will form, and everything that crosses it is guaranteed. Not only never escapes, but also quickly increases the mass, and therefore the size of a forming black hole in a short time. It can absorb the entire mass of any object from which it was formed, and then a black hole will also appear, of course. There may be other exotic ways of forming black holes, but it is believed that the above are responsible for the vast majority of existing black holes in the observable universe. As you probably noticed, all these methods have something in common. They are based on ordinary matter consisting of atoms and their components. This becomes even more surprising when you consider a number of facts. Ordinary matter is only 1/1/6 of the total mass of the universe, and dark matter makes up the remaining 5/6. Both normal and dark matter experience gravitational force equally accurately also, obeying the laws of gravity of Newton and Einstein. In any environment where there is an abundant amount of normal matter, for example, in a galaxy like the Milky Way, there is much more dark matter in general with a ratio of at least 5:1. But why then ordinary matter can form black holes so effectively and dark matter does not? The key lies not in the force of gravity, but in other forces such as friction and collisions that depend on electromagnetic interactions. Ordinary matter experiences this force, but dark matter does not. When a galaxy is formed, dark and ordinary matter are usually formed in it in the above-mentioned ratio of 5:1 on average. This happens throughout the cosmos, like all particles under the influence of gravity. Both matter are attracted to the center of the gravitational potential, and in this direction they accelerate. But here the most interesting thing begins when dark matter penetrates through the galaxy. There is no friction, heating interacting with electromagnetic radiation, and there is no possibility to exchange energy or with other existing particles inside the galaxy. It will remain in a slow orbit with a large angular momentum, and it may take about 1 billion years to form a single complete ellipse. But ordinary matter has everything that dark matter lacks. It collides with other particles of baryonic matter that can exchange energy, and momentum particles can collide, which leads to kinetic losses. They experience friction when they heat up when interacting with other particles of ordinary matter reacting to radiation. But in the aggregate, everything these phenomena lead to a serious difference that can be summarized as follows. Ordinary matter loses momentum and angular momentum and sinks into the core of the galaxy, while dark matter always remains diffusely distributed in a vast space. Creating a halo around the galaxy, ordinary matter forms separate, dense, small clumps, while dark matter forms rare clumps, but mostly very large sizes without a mechanism by which it can transmit angular momentum. Dark matter will never be able to even approach the density necessary for the creation of an event horizon, and therefore a black hole of a star with dark matter does not exist. Therefore, dark matter cannot have a core collapse. There are no regions that would ever collect enough dark matter to attract light in this region back to itself, which means that there cannot be dark matter that has undergone direct collapse. And there are no stellar remnants or other relatively dense objects made of dark matter, and therefore there is no way of collision between objects rich in dark matter that lead to the formation of a black hole. All mechanisms with the methods by which ordinary matter can collapse into a black hole do not.